pick up anything, a book, a cup, a stone, you feel its weight, you feel its mass, and instinctively you believe you're feeling the amount of stuff inside it, the physical material it's made of. But here's what quantum physics has revealed, and it's one of the most unsettling discoveries in all of science. Mass is not made of stuff. When physicists looked inside protons and neutrons, the particles that make up nearly all the mass in your body, they found something that defies common sense. The tiny quarks inside a proton account for less than 1% of its total mass. Less than 1%. So where does the other 99% come from? The answer involves invisible fields that fill all of space, energy trapped by the strongest force in nature, and a complete rethinking of what it even means for something to have mass. Tonight, we're going to find out what mass actually is. Before we go any further, if you find this kind of deep exploration fascinating, a quick like or subscribe really helps the channel grow. It's a small thing for you, but it makes a huge difference for me. Now, let's begin. You've understood mass your entire life, or at least you thought you did. When you pick up a bowling ball, it feels heavy. It resists when you try to move it. It takes effort to lift, effort to throw, effort to stop once it's rolling. A tennis ball, by contrast, feels light. You can toss it effortlessly. You can catch it without bracing yourself. The difference between these two objects, the reason one feels heavy and the other feels light, is mass. And if someone asked you what mass is, you'd probably give an answer that sounds perfectly reasonable. Mass is the amount of matter in an object, the amount of stuff. The bowling ball has more stuff packed inside it than the tennis ball, and that's why it's heavier. That's the intuitive answer. That's what most of us learned in school, and it works beautifully in everyday life. A brick has more mass than a feather. A car has more mass than a bicycle. A planet has more mass than a pebble. More stuff, more mass. Simple. This idea feels so natural, so obvious, that most people never question it. Mass is substance. Mass is material. Mass is the physical stuff that fills an object and gives it weight. And for centuries, this intuition served science well. It guided engineers building bridges and ships. It helped astronomers calculate the orbits of planets. It gave Newton everything he needed to develop his laws of motion and his theory of gravity. When Newton wrote that force equals mass times acceleration, he treated mass as a straightforward quantity. It was a number you could assign to any object, representing how much matter that object contained and how strongly it resisted changes in motion. The more mass something had, the harder it was to push. The more mass something had, the more strongly it pulled on other massive objects through gravity. Mass was the most basic property of matter. It seemed like the simplest concept in all of physics. But quantum physics destroyed this simplicity. Over the past century, physicists have discovered that mass is far stranger, far more mysterious, and far more interesting than anyone imagined. When you look closely enough, when you examine matter at its most fundamental level, the common sense picture of mass as substance falls apart entirely. And what replaces it is one of the most surprising stories in modern science. To understand why, we need to take a journey inward. Not outward into space, not forward into the future, but inward into matter itself. We need to look at what things are made of, layer by layer, and follow the trail all the way down to the deepest level physics can reach. And at each layer, we need to ask the same question. Where does the mass come from? Let's start at the surface. The world around you is made of materials. Wood, metal, water, stone, plastic, glass. These materials have different properties. Some are hard, some are soft. Some are heavy, some are light. Some conduct electricity, some don't. But despite their differences, all of them are made of the same basic ingredients. They're all made of chemical elements. You probably encountered the periodic table in school. It lists all the known elements, from hydrogen, the lightest, to oganesson, the heaviest that has been synthesized. There are about 92 naturally occurring elements on Earth. Everything you see, everything you touch, everything you eat and breathe and drink is made from combinations of these 92 elements. Water is made of hydrogen and oxygen. Table salt is made of sodium and chlorine. The steel in a bridge is mostly iron with small amounts of carbon and other elements mixed in. The air you're breathing right now is mostly nitrogen and oxygen, with traces of argon, carbon dioxide, and other gases. The ancient Greeks were the first to think seriously about what matter is made of at its deepest level. Around 400 BC, a philosopher named Democritus proposed something radical. He suggested that if you took any piece of matter and kept cutting it in half, again and again and again, you'd eventually reach a smallest possible piece, a piece so small it couldn't be divided any further. He called these fundamental pieces atomos, meaning uncuttable. Democritus imagined that everything in the world was built from these tiny, indivisible particles. Different materials had different properties because their atoms had different shapes and arrangements. It was a remarkably modern idea for someone working without microscopes, without laboratories, without any experimental tools at all, just pure reasoning. But Aristotle, arguably the most influential philosopher of the ancient world, disagreed. Aristotle believed matter was continuous. You could always divide it further. There was no smallest piece. Aristotle's authority was so great that his view dominated Western thought for nearly 2,000 years. The idea of atoms was pushed aside, treated as an interesting speculation, but nothing more. It wasn't until the early 1800s that atoms made their comeback. A British chemist named John Dalton noticed something striking about chemical reactions. When elements combined to form compounds, they always combined in fixed ratios by mass. 8 grams of oxygen always combined with 1 gram of hydrogen to make water. This pattern held for every reaction Dalton studied. It made perfect sense if matter was made of atoms with specific, definite masses. If a water molecule always contained exactly 2 hydrogen atoms and 1 oxygen atom, and if oxygen atoms were always 16 times heavier than hydrogen atoms, then the ratio would always be 8:1. The fixed ratios were powerful evidence that atoms were real. But even Dalton thought atoms were the end of the story. He thought atoms were the fundamental building blocks. Solid, indivisible, the smallest things that exist. Mass, in Dalton's picture, was simple. The mass of any object was just the total mass of all its atoms added together. Atoms had mass because they were stuff. They were the stuff, the ultimate substance. There was nothing deeper to explain. Then, in 1897, J.J. Thomson shattered this picture. Working at the Cavendish Laboratory in Cambridge, Thomson was experimenting with cathode rays, streams of particles emitted inside glass tubes when an electric current was applied. By carefully measuring how these rays bent in electric and magnetic fields, Thomson determined that the particles in the rays were far lighter than any known atom. About 1,800 times lighter than a hydrogen atom, the lightest element. Thomson had discovered the electron, a particle smaller than an atom. Atoms were not indivisible after all. They had internal structure. They contained smaller pieces. This was revolutionary. If atoms had parts, then the mass of an atom wasn't fundamental. It was the combined mass of those parts. The question became immediate and pressing. What else was inside an atom? Thomson proposed the plum pudding model, picturing the atom as a blob of positive charge with electrons embedded in it like raisins in a pudding. It was a reasonable guess, but it was wrong. In 1911, Ernest Rutherford proved this by firing alpha particles, which are helium nuclei, at thin gold foil. Most alpha particles passed straight through, which was expected, but occasionally one bounced back at a sharp angle. Some came nearly straight back toward the source. Rutherford was stunned. He later compared it to firing an artillery shell at tissue paper and having it bounce back at you. The only explanation was that almost all the atom's mass and all its positive charge were concentrated in a tiny region at the center. This was the nucleus. The atom was mostly empty space. The electrons orbited far from the nucleus, like planets orbiting a distant star. If you scaled an atom up to the size of a football stadium, the nucleus would be about the size of a small marble sitting at the center of the field. Everything else would be empty. And yet, that tiny marble contained almost all the atom's mass. This was a strange result. The atom was enormous compared to its nucleus, about 10,000 times larger in diameter, but almost all the mass lived in that minuscule core. The electrons buzzing around the vast empty space of the atom contributed almost nothing to its total mass. Already, mass was behaving in unexpected ways. It wasn't spread evenly throughout the atom. It was concentrated in one tiny spot. Over the following decades, physicists probed the nucleus and found it had structure too. The nucleus contained two types of particles: protons, which carried positive electric charge, and neutrons, which carried no charge at all. Both had roughly the same mass, and both were about 1,836 times heavier than an electron. The number of protons determined which element an atom was. Hydrogen had 1 proton, helium had 2, carbon had 6, uranium had 92. Neutrons provided additional mass and helped hold the nucleus together against the repulsive electric force between positively charged protons. So now the picture of mass seemed clear again, just pushed one level deeper. The mass of any object was the mass of its atoms. The mass of each atom was mostly the mass of its nucleus. The mass of the nucleus was the combined mass of its protons and neutrons. And protons and neutrons were the fundamental building blocks. They were the stuff. They were where mass lived. The answer to the question, what is mass made of, seemed to be protons and neutrons. But physics wasn't done digging. In the 1960s, experiments at particle accelerators began revealing something shocking. Protons and neutrons were not fundamental either. They had internal structure. They were made of even smaller particles. The particles inside the proton would come to be called quarks, a whimsical name borrowed from a line in James Joyce's novel Finnegan's Wake. A proton, it turned out, contained 2 up quarks and 1 down quark. A neutron contained 1 up quark and 2 down quarks. These quarks were held together by particles called gluons, which carried the strong nuclear force, the most powerful force in nature. But the story of how quarks were discovered is one of the great detective stories in modern physics. For decades, physicists had assumed protons and neutrons were the end of the line, the final building blocks, the things mass was ultimately made of. Countless experiments had measured their properties with extraordinary precision. They seemed solid, complete, fundamental. But a new generation of accelerators was about to shatter that assumption entirely. The discovery was not clean or immediate. It unfolded over years, and the physicists involved did not agree at first on what they were seeing. The experiments at SLAC in the late 1960s were designed to probe the proton's interior by smashing high-energy electrons into hydrogen targets. The electrons acted like tiny bullets fired at the proton. If the proton were a smooth, uniform blob of matter, the electrons would scatter gently, deflecting at small angles like marbles rolling off a pillow. That's what most physicists expected to see. Instead, the electrons occasionally bounced back at sharp, violent angles. Some ricocheted nearly backward. The scattering pattern looked almost identical to what Rutherford had seen 60 years earlier when he fired alpha particles at gold foil and discovered the atomic nucleus. Something small, hard, and point-like was sitting inside the proton. The physicist Richard Feynman, visiting SLAC during these experiments, immediately grasped the implications. He began calling the hard objects inside the proton partons, meaning simply parts. He didn't commit to what they were. He just recognized that the proton had internal structure. Meanwhile, Murray Gell-Mann and George Zweig had already predicted quarks on purely theoretical grounds, using mathematical patterns in the zoo of particles discovered at accelerators throughout the 1950s and 60s. Gell-Mann had organized dozens of seemingly unrelated particles into elegant geometric patterns based on their properties. The patterns only made sense if each of these particles was built from smaller components combining in specific ways. When the scattering experiments confirmed that hard, point-like objects really did exist inside the proton, and when those objects matched the properties Gell-Mann's quarks were predicted to have, the picture snapped into focus. Feynman's partons and Gell-Mann's quarks were the same thing, seen from different angles. One approach was experimental, the other was theoretical. They converged on the same truth. The proton was not fundamental. It was built from smaller pieces, and those pieces were real. Throughout the 1970s, experiment after experiment at accelerators around the world tested the quark model relentlessly and confirmed it. Quarks were not mathematical abstractions. They were physical entities inside every proton and neutron in every atom of your body. But even as this became clear, a puzzle emerged immediately. If quarks existed inside the proton, why had no one ever seen a free quark? Every other subatomic particle that had been discovered could be produced in isolation. Electrons, protons, neutrons, pions, muons. All of them could be created and detected as individual particles flying through a detector. Quarks could not. No experiment, no matter how energetic, ever produced a lone quark. They always appeared in groups, bound inside composite particles. This was deeply strange, and explaining it required understanding something about the strong force that set it apart from every other force in nature. So the trail of mass now went even deeper. The mass of any object was the mass of its atoms. The mass of each atom was mostly the mass of its nucleus. The mass of the nucleus was the combined mass of its protons and neutrons. And the mass of each proton and neutron was the combined mass of its quarks. Quarks were the stuff. Quarks were where mass lived. Or so you might think. And this is where the story takes its most dramatic turn. Because when physicists measured the masses of the quarks inside a proton, they found something deeply unsettling. A proton has a mass of about 938 mega-electron volts divided by the speed of light squared. That's the standard unit particle physicists use, and it corresponds to roughly 1.67 times 10 to the negative 27th kilograms, an incredibly tiny number, but a very precise one. We know the proton's mass with extraordinary accuracy. Now, a proton contains 2 up quarks and 1 down quark. An up quark has a mass of about 2.2 mega-electron volts divided by the speed of light squared. A down quark has a mass of about 4.7 mega-electron volts divided by the speed of light squared. Add them up. 2 up quarks at 2.2 each gives 4.4. 1 down quark at 4.7 gives 4.7. Total quark mass inside a proton, roughly 9.1 mega-electron volts divided by the speed of light squared. The proton's total mass is 938. The quarks inside it contribute about 9. that's less than 1%. Not 90%, not 50%, not even 10%. Less than 1% of the proton's mass comes from the mass of its quarks. Let that sink in for a moment. For centuries, we've been chasing mass deeper and deeper into matter, always assuming that the mass of the whole was simply the mass of its parts. And at every level, that seemed to work. The mass of a brick was the mass of its atoms. The mass of atoms was the mass of their nuclei. The mass of nuclei was the mass of their protons and neutrons. But when we finally got to the deepest level we can probe, the pattern broke completely. The mass of a proton is not the mass of its quarks. The quarks barely contribute anything. More than 99% of the proton's mass comes from something else entirely. Not from substance, not from material, not from stuff in any sense you've ever imagined. And since protons and neutrons make up nearly all the mass of every atom, and atoms make up everything around you, this means more than 99% of the mass of your body, of this planet, of every object you've ever touched, comes from something that is not material substance. So what is it? What is the other 99%? Where does most of the mass in the universe actually come from? Before we can answer that, we need to understand something crucial. Not all particles get their mass the same way. And this is the key insight that modern physics has given us. There are two fundamentally different categories of particles, and they acquire mass through completely different mechanisms. The first category is elementary particles. These are particles that, as far as we know, have no internal structure. They are not made of anything smaller. They are the bottom of the chain. Quarks are elementary particles. Electrons are elementary particles. Photons, the particles of light, are elementary particles. Neutrinos, the ghostly particles that pass through your body by the trillions every second, are elementary particles. The list also includes muons, tau particles, and several types of force-carrying particles. These particles are described by the Standard Model of Particle Physics, the most successful and precisely tested theory in the history of science. The second category is composite particles. These are particles made of smaller particles bound together. Protons are composite particles, made of quarks and gluons. Neutrons are composite particles, also made of quarks and gluons. Atoms are composite. Molecules are composite. You are composite, built from layer upon layer of smaller things. Here's what matters. Elementary particles and composite particles get their mass in fundamentally different ways. The mass of an elementary particle comes from one mechanism. The mass of a composite particle comes from a completely different mechanism. And confusing the two, mixing them up, treating them as the same thing, is one of the biggest misunderstandings in popular science. For elementary particles, the question of mass leads to one of the most remarkable discoveries of the 20th century. There is a field, invisible and pervasive, filling every cubic centimeter of the universe. It exists everywhere, in the emptiest void of deep space, in the densest core of a neutron star, right here in the room where you're sitting. And this field is the reason elementary particles like electrons and quarks have mass at all. This is the Higgs field, and understanding it will change how you think about mass forever. But the Higgs field is only part of the story, because the Higgs field gives mass to elementary particles, and those masses are tiny. The electron's mass is minuscule. The quark masses are small. These Higgs-given masses account for less than 1% of the mass in ordinary matter. The rest, the overwhelming majority, comes from something wilder. Something involving the most violent force in nature. A seething storm of energy trapped inside every proton and every neutron in existence. Mass, it turns out, is not one thing. It does not have one origin. It does not come from one source. The mass of an electron comes from a different mechanism than the mass of a proton. The mass of a quark comes from a different mechanism than the mass of an atom. And none of these mechanisms involve mass being made of some smaller substance. At no level is mass simply stuff. At every level, it's something more subtle, more surprising, and more profound. The story of mass is really two stories. One about fields that fill all of space and give elementary particles their identity, and another about energy so intense and confined that it manifests as the weight you feel when you pick up a stone. These two stories are connected. They're both rooted in quantum physics, but they operate through different principles, and understanding each one separately is essential before you can see the full picture. We've spent centuries looking for the substance of mass. We kept digging deeper, assuming that at the bottom we'd find the ultimate stuff, the thing mass is made of. Instead, we found that mass isn't made of anything, not in the way we expected. Mass is not a substance, it's a property, a measurable, quantifiable, real property of particles and systems, but not a substance you can point to and say, there, that is what mass is made of. This is the deepest shift in understanding that quantum physics demands. Not just that the world is strange at small scales, not just that particles behave like waves or that measurement affects outcomes, but that one of the most familiar, most everyday, most taken for granted properties of matter, the mass you feel every time you lift a cup of coffee, has origins so unlike our intuitions that it forces us to rethink what matter even is. The answers lie ahead. First, we need to understand the Higgs field and how it gives mass to the lightest, most fundamental particles in existence. Then we need to confront the strong nuclear force and the extraordinary phenomenon that generates more than 99% of the mass in your body. And finally, we need to put it all together and see what mass truly is. Not as a substance, but as something stranger and more beautiful than substance could ever be. To understand where the mass of elementary particles comes from, we first need to understand something that most people have never heard of, even though it forms the very foundation of modern physics. We need to understand quantum fields. You've heard of particles, electrons, protons, photons. These are the building blocks you learned about in school. Tiny objects, little specks of matter or energy, zipping around through space. That's the picture most people carry in their heads. Particles are things. They're objects. They exist at specific locations and move from place to place. But modern physics tells a very different story. In the deepest and most successful framework we have for describing nature, particles are not the fundamental entities. Fields are. Particles are what you get when a field is disturbed in a particular way. They are ripples, excitations, temporary patterns of vibration in something much larger and more fundamental than any individual particle. Quantum fields are like the ocean. They're the fundamental substance of reality, and particles are like waves on that ocean. They're disturbances in the fields, temporary patterns of energy that we detect and measure and call electrons or photons or quarks. But the fields come first. The fields are what's real at the deepest level. The particles are consequences. This idea, called quantum field theory, was developed over the course of the 20th century by some of the greatest minds in physics. Paul Dirac took the first steps in the late 1920s when he combined quantum mechanics with Einstein's special relativity and predicted the existence of antimatter before it was ever observed. Richard Feynman, Julian Schwinger, and Shinichiro Tominaga independently developed quantum electrodynamics in the late 1940s, creating the first fully successful quantum field theory. It described how electrons interact with photons with extraordinary precision, matching experiments to more than 10 decimal places. This remains one of the most accurate predictions in all of science. In quantum field theory, every type of particle corresponds to a different field. There is an electron field permeating all of space. When this field is excited in a certain way, we observe an electron. There is a photon field, which is really the electromagnetic field described quantum mechanically. When it vibrates, we detect photons, which are particles of light. There is an up quark field, a down quark field, a neutrino field, and fields for every other elementary particle in the Standard Model. Each field fills the entire universe. Each field exists everywhere. And what we call particles are simply localized vibrations in these fields. Here's an analogy. Imagine a calm lake at dawn. The surface is perfectly still. No ripples, no disturbances. This is like a quantum field in its lowest energy state, what physicists call the vacuum state. Now drop a pebble into the lake. A ripple spreads outward. That ripple is like a particle. It has a definite location. It carries energy. It moves. But it's not a separate thing from the lake. It's the lake, temporarily excited. If you drop two pebbles, you get two ripples. They can interact. They can pass through each other or combine. This is like two particles being created, interacting, and perhaps annihilating each other. The lake is always there. The ripples come and go. Now, here's a critical question. What determines whether a ripple in a particular field corresponds to a massive particle or a massless one? Why does a ripple in the electron field behave like a particle with mass, while a ripple in the electromagnetic field behaves like a photon with no mass at all? What is it about some fields that makes their excitations heavy and other fields that makes their excitations weightless? The answer leads us to one of the most remarkable discoveries in the history of physics. There is another field, a field unlike any other, that permeates all of space and interacts with certain particles in a way that gives them mass. This is the Higgs field, and understanding it requires letting go of almost everything your intuition tells you about how fields should behave. Every other quantum field in its lowest energy state, its vacuum state, has a value of 0. Think about the electromagnetic field. In empty space, far from any charges or magnets or light sources, the electromagnetic field is 0. There are no photons, no electric or magnetic forces. The field is in its ground state, and that ground state is 0. If you want to create a photon, you need to add energy to the field, excite it above 0. The Higgs field is different. It is fundamentally, profoundly different. In its lowest energy state, the Higgs field does not sit at 0. It has a non-zero value everywhere in the universe. Not because something is exciting it, not because energy is being pumped into it. Its natural resting state, the state of lowest possible energy, is a state where the field has a constant, uniform, non-zero value throughout all of space. This might sound like a small technical detail. It is not. It changes everything. Imagine walking through air. Air fills the room around you, but you barely notice it. It exerts almost no resistance when you move slowly. Now imagine walking through waist-deep water. Suddenly, every step takes effort. The water pushes back against you. It slows you down. It resists your motion. You feel heavier. You feel more sluggish. Not because you've gained weight, but because the medium you're moving through interacts with you and creates resistance. The Higgs field does something loosely analogous for elementary particles. Because the Higgs field has a non-zero value everywhere, particles that interact with it are constantly immersed in it. They cannot escape it. There is no region of space where the Higgs field is absent. And for particles that couple to the Higgs field, this constant interaction has a profound consequence. It gives them inertia. It gives them resistance to acceleration. It gives them what we measure as mass. An electron moving through space is constantly interacting with the Higgs field. This interaction doesn't slow the electron down. It's not friction. The electron doesn't lose energy to the Higgs field. But the interaction changes the electron's fundamental character. Without the Higgs field, the equations of the Standard Model predict that the electron would be massless. It would travel at the speed of light, just like a photon. It would have energy and momentum, but no rest mass. With the Higgs field switched on, with its non-zero vacuum value filling all of space, the electron acquires rest mass. It slows below light speed. It becomes the particle we know, the particle that orbits atomic nuclei and makes chemistry possible. The same is true for quarks. Without the Higgs field, up quarks and down quarks would be massless. They would zip around at the speed of light. But because the Higgs field is always present, always non-zero, quarks interact with it and acquire small but definite rest masses. An up quark gets a rest mass of about 2.2 mega-electron-volts divided by the speed of light squared. A down quark gets about 4.7 mega-electron-volts divided by the speed of light squared. These masses are small, tiny compared to the mass of a proton, but they are real and they come from the Higgs field. Different particles interact with the Higgs field at different strengths. This is crucial. The strength of the interaction determines how much mass a particle gets. An electron interacts weakly with the Higgs field, so it acquires a small mass, about 0.511 mega-electron-volts, divided by the speed of light squared. A top quark interacts very strongly with the Higgs field, so it acquires an enormous mass, about 173 giga-electron-volts, divided by the speed of light squared. That makes the top quark roughly 338,000 times more massive than the electron, even though they're both elementary particles. The difference in mass comes entirely from how strongly each particle couples to the Higgs field. Why do different particles interact with the Higgs field at different strengths? This is one of the open questions in physics. The Standard Model doesn't predict these interaction strengths from first principles. It measures them experimentally and writes them into the equations as numbers, called Yukawa coupling constants. Each particle has its own coupling constant, and therefore its own mass. But we don't know why those particular numbers are what they are. We don't know why the electron is light and the top quark is heavy. We just know that the Higgs field treats them differently. Understanding the pattern behind these coupling constants, if there is a pattern, would be a major breakthrough in particle physics. Now, there is a very common misconception that needs to be addressed head-on. Many people, when they first hear about the Higgs mechanism, come away believing that mass is made of Higgs bosons. This is wrong. Emphatically, clearly, fundamentally wrong. And the confusion is understandable, because the Higgs boson got an enormous amount of media attention when it was discovered in 2012 at the Large Hadron Collider at CERN. It was called the God particle in headlines around the world. People assumed the Higgs boson was what gave everything mass, but that's not how it works. The Higgs boson is a particle. It's an excitation of the Higgs field, just as a photon is an excitation of the electromagnetic field. When you disturb the Higgs field, when you pump enough energy into it, you can create a Higgs boson. This is what the Large Hadron Collider did. It smashed protons together at enormous energies, and, in the debris, occasionally produced a Higgs boson, with a mass of about 125 giga-electron-volts divided by the speed of light squared. The Higgs boson exists for an incredibly brief moment, about 1.6 times 10 to the negative 22nd seconds, before it decays into other particles. But the Higgs boson is not what gives particles mass. The Higgs field is. The Higgs boson is just evidence that the Higgs field exists. Think of it this way. Imagine you discover a single musical note ringing through a concert hall. That note tells you a piano exists somewhere in the room, but the note is not the piano. The note is a brief vibration produced by the piano. The piano itself sits there whether anyone strikes a key or not. The Higgs boson is the note. The Higgs field is the piano. Discovering the boson proved the field exists, but the boson is not the reason particles have mass. The field, with its constant non-zero value filling all of space, is what does the work. This distinction matters because the Higgs boson is extremely rare and short-lived. It plays no role in everyday physics. You will never encounter a Higgs boson in your daily life. But the Higgs field is everywhere, always, filling every point in space. It's the field that matters for mass, not the boson. The history of how this mechanism was discovered is itself a remarkable story. In the early 1960s, physicists were struggling with a serious theoretical problem. They had developed elegant mathematical frameworks for describing the fundamental forces of nature using quantum field theory. These frameworks, called gauge theories, were beautiful and powerful. They described the electromagnetic force perfectly. And physicists suspected similar mathematics could describe the weak nuclear force, the force responsible for certain types of radioactive decay. But there was a fatal flaw. Gauge theories, in their simplest form, only work if the force-carrying particles are massless. Photons, which carry the electromagnetic force, are indeed massless. So the theory worked perfectly for electromagnetism. But the particles that carry the weak force, the W and Z bosons, are heavy. The W boson has a mass of about 80.4 giga-electron-volts divided by the speed of light squared. The Z boson has a mass of about 91.2 giga-electron-volts divided by the speed of light squared. These are enormous masses, roughly 86 and 97 times the mass of a proton. If you simply wrote these masses into the equations by hand, the mathematical consistency of the theory collapsed. The calculations produced infinities that couldn't be removed. The theory became useless. You couldn't just declare that the W and Z bosons were massive. The mathematics forbade it. You needed a mechanism, a way for the W and Z bosons to acquire mass without breaking the mathematical structure of the gauge theory. You needed the math to generate mass naturally, organically, from within the theory itself. In 1964, several groups of physicists independently proposed a solution. Peter Higgs in Edinburgh published a paper. François Englert and Robert Brout in Brussels published a paper. Gerald Guralnick, Carl Hagen and Tom Kibble in London published a paper. All three groups, working independently, proposed essentially the same idea. If you added a new field to the theory, a field with a non-zero vacuum value, a field that interacted with the W and Z bosons, then those bosons would naturally acquire mass through their interaction with this field. The mathematical consistency of the gauge theory would be preserved. The infinities would cancel. The theory would work. This was the Higgs mechanism, and it solved not just the problem of the W and Z boson masses, but the problem of mass for all elementary particles. Any particle that interacted with this new field would acquire mass proportional to the strength of the interaction. Particles that didn't interact with the field would remain massless. It took nearly 50 years to confirm the theory experimentally. The Higgs field, being a quantum field, should have its own excitation, its own particle. This was the Higgs boson. Theorists predicted its existence, but couldn't predict its exact mass. The only way to find it was to build particle accelerators powerful enough to produce it. The Large Hadron Collider at CERN, a ring 27 kilometers in circumference, straddling the border between France and Switzerland, was specifically designed, in part, to search for the Higgs boson. On July 4, 2012, scientists at CERN announced the discovery of a new particle with a mass of about 125 giga-electron volts divided by the speed of light squared. its properties match the predicted Higgs boson. Peter Higgs and François Englert were awarded the Nobel Prize in Physics in 2013. Robert Brout had passed away in 2011 and could not share the prize. The discovery confirmed that the Higgs field is real. It fills all of space. It has a non-zero value everywhere. And it is the reason elementary particles like electrons, quarks, and the W and Z bosons have rest mass. Now, let's be precise about what kind of mass the Higgs field gives. It gives rest mass. This is the mass a particle has when it's sitting still, when it's not moving relative to you. Rest mass is an intrinsic property of a particle. It doesn't change depending on how fast the particle moves. It doesn't depend on where the particle is. It's a fundamental characteristic, like electric charge. Rest mass is what determines a particle's minimum energy. Einstein's famous equation, E equals mc squared, tells you the energy equivalent of rest mass. A particle at rest still has energy, and that energy equals its rest mass multiplied by the speed of light squared. This is the energy locked inside the particle's very existence, the energy it has just by being a massive particle rather than a massless one. Rest mass is also what prevents a particle from reaching the speed of light. Any particle with non-zero rest mass would require infinite energy to be accelerated to light speed. This is why electrons always move slower than light. This is why quarks always move slower than light. Their rest masses, given by the Higgs field, ensure they can never reach that ultimate speed. But here's something important that many people misunderstand. Having zero rest mass does not mean having zero energy. Photons have zero rest mass, but they absolutely have energy. You feel the energy of photons every time sunlight warms your skin. The energy of a photon depends on its frequency. Blue light has more energy per photon than red light. Gamma rays have enormously more energy than visible light. Photons also carry momentum. Light pushes on things. Solar sails, thin reflective sheets proposed for spacecraft propulsion, work because photons transfer momentum when they bounce off a surface. So photons have energy, they have momentum, they exert force. They can heat objects and break chemical bonds and knock electrons out of atoms. But they have no rest mass. They do not interact with the Higgs field. They are completely transparent to it. The Higgs field has no effect on photons whatsoever. And because photons have no rest mass, they must always travel at the speed of light. They are born at light speed, and they remain at light speed until they are absorbed. They cannot slow down. They cannot stop. A universe without the Higgs field would be a universe where all elementary particles behaved like photons, massless and moving at the speed of light. This reveals something profound about the Higgs field's role. The Higgs field doesn't create mass from nothing. What it does is break asymmetry. In the fundamental equations of the Standard Model, before the Higgs field acquires its non-zero value, all elementary particles are massless. The equations are symmetric. No particle is heavier than any other because none of them have mass. They're all identical in that one respect. They all move at the speed of light. When the Higgs field settles into its non-zero vacuum state, this symmetry breaks. Particles that couple to the Higgs field acquire mass. Particles that don't remain massless. The once identical particles become different from one another. Some become heavy, some light, some stay weightless. The symmetry is broken and diversity emerges. This process is called spontaneous symmetry breaking, and it is believed to have occurred in the very early universe, likely within the first trillionth of a second after the Big Bang, when the universe cooled below a critical temperature and the Higgs field transitioned from 0 to to its current non-zero value. That critical temperature was roughly 1,000 trillion degrees, a heat so extreme that it existed for only a fleeting instant after the birth of the universe, before the cosmos cooled past it forever. Before that transition, the universe was a fundamentally different place. All elementary particles were massless. They all travelled at the speed of light. There were no atoms, because electrons had no mass and couldn't be captured into orbits. There was no chemistry. There was no structure. Just a blazing hot soup of massless particles streaming through space at maximum speed. Then the Higgs field turned on. Not literally, not like a switch, but in the sense that the universe cooled enough for the field to settle into its non-zero state. And suddenly, or rather over a brief transition period, particles began acquiring mass. Electrons slowed below light speed. Quarks became sluggish enough to be bound together. The raw ingredients for matter came into existence. Without the Higgs field, the universe would contain energy and radiation, but no stable matter. No atoms, no molecules, no stars, no planets, no chemistry, no biology, no you, and no me. The Higgs field made structure possible by giving elementary particles the rest mass they needed to combine into larger, stable systems. But here's where we need to be extremely careful. Because the Higgs field's contribution to the mass of everyday matter is surprisingly small. The electron's rest mass, given by the Higgs field, is about 0.511 mega-electron volts divided by the speed of light squared. That's tiny. In an atom of hydrogen, the electron contributes roughly 1/20th of 1% of the atom's total mass. The vast majority of the atom's mass lives in the nucleus, in the proton. And as we discussed earlier, the quark masses inside the proton, also given by the Higgs field, add up to less than 1% of the proton's total mass. So the Higgs field, despite its enormous importance for the existence of matter, despite being the mechanism that gives elementary particles their rest mass, is directly responsible for less than 1% of the mass in ordinary matter. Less than 1% of the mass in your body comes from the Higgs mechanism. The rest, the overwhelming majority, comes from somewhere else entirely. And this is the part of the story that most popular accounts skip over, the part that is arguably even more fascinating than the Higgs field itself. Because the other 99% of your mass doesn't come from any particle's rest mass at all. It doesn't come from substance or material or stuff in any familiar sense. It comes from energy. Raw, furious, trapped energy, bound inside every proton and neutron by the most powerful force in nature. The Higgs field is essential. Without it, elementary particles would be massless, and the universe would have no stable matter. But the Higgs field is not the main source of mass in the world around you. It's a small contributor, giving quarks and electrons the tiny rest masses they need to exist as distinct particles. The heavy lifting, the generation of more than 99% of the mass you feel when you pick up a stone or step on a scale, is done by something else. Something far more violent and far more strange. And understanding it requires us to look inside the proton and confront the extraordinary dynamics taking place within the smallest structures in atomic matter. The Higgs field gave us the vocabulary of mass. It explained how elementary particles acquire rest mass through field interactions. It showed us that mass is not an intrinsic, unexplainable property that particles simply have, but a consequence of a specific mechanism involving a specific field. Mass has an origin. It comes from somewhere. And for elementary particles, it comes from the Higgs field. But the vocabulary is only the beginning. The real story, the story of where almost all the mass in the observable universe actually comes from, requires a completely different domain of physics, one involving quarks confined in spaces smaller than a trillionth of a millimeter, gluons multiplying and annihilating in a frenzy of quantum activity, and the deep relationship between energy and mass that Einstein captured in an equation but never could have imagined would manifest in such a wild and dramatic way. We now come to the heart of the mystery, the part of the story that most people never hear. Because when you read about mass in popular science, you almost always hear about the Higgs field. You hear about how the Higgs gives particles their mass. You see diagrams of particles wading through an invisible field, like people pushing through a crowd. And the impression you're left with is that the Higgs field explains mass. Problem solved, mystery over. But the Higgs field is only responsible for a tiny fraction of the mass in the world around you. We've already seen the numbers. The quarks inside a proton have Higgs-given rest masses totaling about 9 mega-electron volts divided by the speed of light squared. The proton itself has a mass of about 938 mega-electron volts divided by the speed of light squared. The quarks account for less than 1%. So more than 99% of the proton's mass comes from something that has nothing to do with the Higgs field at all. And protons and neutrons make up nearly all the mass in atoms. Electrons, despite being essential for chemistry and for the structure of matter, are incredibly light. An electron's mass is only roughly 1/1800th the mass of a proton. In any atom, the nucleus, which is made of protons and neutrons, accounts for more than 99.9% of the atom's total mass. So when you step on a scale, when you feel the weight of your own body, when you lift a rock or a chair or a glass of water, the mass you're feeling is almost entirely the mass of protons and neutrons. And more than 99% of that mass does not come from any particle's rest mass. It comes from something else. To understand what that something else is, we need to look inside the proton. And what we find in there is one of the wildest environments in all of physics. A proton is incredibly small. Its diameter is roughly 1 femtometer, which is 1/millionth of 1/billionth of a meter. To put that in perspective, roughly 100,000 protons laid side by side would barely span the width of a single atom. The proton is to an atom what a pinhead is to a cathedral. But despite its minuscule size, the proton's interior is anything but simple. It's a seething, churning, violently dynamic place, filled with activity so intense that it defies ordinary description. Inside the proton, you find 3 valence quarks. These are the 2 up quarks and 1 down quark we discussed earlier. They're the quarks that give the proton its identity, its electric charge, and certain quantum properties. But these 3 quarks are not sitting still. They are not calmly occupying fixed positions like balls in a bowl. They are moving at speeds close to the speed of light, confined within a space roughly 1 femtometer across. They ricochet and whirl within this impossibly small volume, carrying tremendous kinetic energy. And the quarks are not alone. Between them, binding them together, holding them in their frenzied confinement, is a storm of gluons. Gluons are the particles that carry the strong nuclear force, just as photons carry the electromagnetic force. But gluons behave very differently from photons. And this difference is the key to understanding where most of the mass in the universe comes from. The force that binds quarks together is described by a theory called quantum chromodynamics, often abbreviated as QCD. It's the quantum field theory of the strong force, and it is one of the most mathematically challenging and physically rich theories ever developed. The name chromodynamics comes from the Greek word for color, because the strong force operates through a property called color charge. This has nothing to do with actual colors. Quarks don't literally glow red or blue. Color charge is just a label physicists use for the strong force equivalent of electric charge. In electromagnetism, particles can have positive or negative electric charge. In the strong force, Quarks carry one of three types of color charge, whimsically named red, green, and blue. Just as electrically charged particles attract and repel each other through the exchange of photons, color-charged quarks attract and repel each other through the exchange of gluons. But here's where things get dramatically different. Photons do not carry electric charge. A photon mediates the electromagnetic force between charged particles, but the photon itself is electrically neutral. It doesn't interact with itself. It doesn't attract or repel other photons through electromagnetism. Gluons are different. Gluons carry color charge. A gluon is not neutral in the strong force. It actively participates in the force it carries. This means gluons interact with each other. They attract each other. They can emit more gluons. They form chains and webs and tangled networks of strong force field lines. This property, the self-interaction of gluons, makes the strong force utterly unlike any other force in nature. And it leads to consequences that are almost impossible to picture intuitively. In electromagnetism, if you have two opposite electric charges and you pull them apart, the force between them weakens. The electric field lines spread out. At greater distances, the force fades. Pull the charges far enough apart, and the force becomes negligible. This is why electromagnetism has long range. It extends across vast distances, but it weakens with distance. The strong force works in exactly the opposite way. When two quarks are close together, the strong force between them is relatively weak. They can move around almost freely within a very small region. Physicists call this property asymptotic freedom, and its discovery by David Gross, Frank Wilczek, and H. David Politzer in 1973 earned them the Nobel Prize in Physics in 2004. At very short distances, quarks behave almost as if they're free particles. The strong force barely tugs on them. But as you try to pull two quarks apart, the force between them doesn't weaken, it strengthens. The gluon field lines between the quarks don't spread out like electric field lines. Instead, they squeeze together. They form a narrow tube, a string-like concentration of gluon field energy stretching between the separating quarks. And as you pull harder, as the distance increases, the energy stored in that tube increases. The force doesn't fade, it stays constant or even grows. You pull, and the gluon tube stretches and stores more and more energy. Think of it like stretching a rubber band. The farther you stretch it, the more energy you put into it. The band resists more and more. With a rubber band, at some point, the band snaps. With the strong force, something analogous happens, but even stranger. When you've put enough energy into the gluon tube, when you've stretched it far enough, the energy in the tube becomes so large that it spontaneously creates new quarks. The energy converts into matter. The gluon tube snaps, and at the breaking point, a new quark and a new antiquark appear. You started with two quarks and tried to pull them apart. You ended up with four quarks, rearranged into two new quark pairs. You never successfully isolated a single quark. You can never get a quark alone. This phenomenon is called confinement. Quarks are permanently confined inside composite particles. You cannot extract a single quark and hold it up and examine it in isolation. It's not a matter of technology. It's not that our tools aren't good enough. It's a fundamental law of nature. The strong force simply won't allow it. Every time you try to separate quarks, the energy you invest creates new quarks that immediately pair up, forming new composite particles. Quarks always exist in groups, bound together by gluons, locked inside particles called hadrons. The permanence of confinement deserves emphasis. In the entire history of experimental physics, across tens of thousands of experiments at dozens of particle accelerators over more than half a century, no one has ever observed a free quark. Not once. Not a hint. Not a marginal signal that might be a quark if you squinted at the data. The absence is total and absolute. Every collision that has ever been recorded, every decay that has ever been measured, every cosmic ray that has ever struck a detector, has produced quarks only in bound combinations. The strong force does not merely prefer to keep quarks confined, it demands it. Confinement appears to be an absolute law of nature, as inviolable as the speed of light. Imagine a force so powerful that it literally forbids its own constituents from existing independently. Electromagnetism doesn't work this way. You can isolate a positive charge from a negative charge. Gravity doesn't work this way. You can separate two massive objects and move them as far apart as you like. But the strong force says no. You may not have a quark alone. Try, and the universe will create new quarks from pure energy rather than allow it. The force rewrites the rules of what can exist rather than permit a single violation of confinement. There is something almost alive about this behavior, a relentless enforcement mechanism that operates at every energy scale ever tested. There are two main types of hadrons: baryons, which contain 3 quarks, and mesons, which contain 1 quark and 1 antiquark. Protons and neutrons are baryons. Pions and kaons are mesons. There are hundreds of known hadrons, all made of quarks bound by gluons, all governed by QCD. Now, confinement is directly connected to the origin of mass inside the proton. Here's how. The 3 valence quarks inside a proton are confined to a space roughly 1 femtometer across. They cannot escape. The strong force holds them in, and because they're confined to such a tiny space, the Heisenberg uncertainty principle, the same principle from quantum mechanics that says you can't know a particle's position and momentum simultaneously with perfect precision, guarantees that the quarks must have very high momentum. The more precisely a particle is localized, the more uncertain its momentum. Confined to 1 femtometer, the quarks have enormous momentum. They move at speeds approaching the speed of light. This is not a gentle vibration. This is violent, relativistic motion. The quarks are not slowly drifting inside the proton. They are screaming through it at nearly the fastest speed possible, rebounding off the walls of their confinement, constantly changing direction. The kinetic energy associated with this motion is enormous, and remember Einstein's equation, E equals mc squared. Energy and mass are equivalent. They are 2 expressions of the same thing. Any system that contains energy behaves as if it has mass. This isn't a metaphor, it's not an approximation, it's exact physics. If you have a box filled with light, the box weighs more than the same box empty, because the light inside has energy, and that energy contributes to the system's mass. Not much in the case of everyday light, but the principle is absolute. Energy has mass, mass is energy. Inside the proton, the kinetic energy of the quarks, the energy of their frenzied relativistic motion, contributes real, measurable mass to the proton. This is not the rest mass of the quarks. It's not the Higgs given mass. It's the energy of motion, converted into mass through Einstein's equivalence. But the quark's kinetic energy is only part of the story. Perhaps the larger contribution comes from the gluon field itself. The gluon field inside the proton is extraordinarily intense. Remember, gluons carry color charge. They interact with each other. They are constantly being emitted and absorbed by the quarks, and they're also emitting and absorbing other gluons. The interior of the proton isn't just 3 quarks whizzing around. It's 3 quarks embedded in a dense, turbulent cloud of gluons, with gluons constantly appearing and disappearing, splitting into pairs, merging back together. The gluon field energy, the energy stored in this roiling storm of strong force field activity, is enormous. In fact, gluons are massless. They have 0 rest mass. Like photons, gluons acquire no mass from the Higgs field. And yet, the energy of the gluon field inside the proton contributes significantly to the proton's total mass. Massless particles carrying enormous energy, generating measurable mass. This is Einstein's equation at work in the most dramatic way imaginable. The gluons have no rest mass, but their energy is real, and that energy behaves as mass. So the mass of the proton comes from three main sources. First, the rest masses of the quarks given by the Higgs field. This contributes less than 1%. Second, the kinetic energy of the quarks, the energy of their violent confined motion. This contributes a significant fraction. Third, the energy stored in the gluon field, the energy of the strong force itself binding the quarks together and churning with constant quantum activity. This contributes the largest share. When physicists say that most of the proton's mass comes from energy, this is what they mean. Not a vague philosophical statement, not a loose metaphor, a precise physical fact. The energy of quark motion and gluon field dynamics through Einstein's mass-energy equivalence generates more than 99% of the proton's measured mass. The mass is real. You can weigh it, you can measure it, you can feel it when you lift a heavy object. But it comes from energy, not from substance. There is also a subtler contribution that deserves mention. The quantum vacuum inside the proton is not empty. Even in ordinary empty space, quantum fields fluctuate. Virtual particles pop in and out of existence constantly, borrowing energy for brief moments before disappearing. Inside the proton, these quantum fluctuations are especially intense because of the strong gluon field. Virtual quark-antiquark pairs constantly appear and vanish inside the proton. These are sometimes called C-quarks, to distinguish them from the three valence quarks that define the proton's identity. At any given instant, the proton contains not just three quarks, but a vast, fluctuating population of virtual quarks, virtual antiquarks, and virtual gluons, all contributing energy, all contributing to the proton's total mass. To get a sense of just how crowded the proton's interior really is, consider what high-energy scattering experiments have revealed about its contents. When physicists probe the proton at very high energies, they can resolve finer and finer details of its internal structure. And what they find is astonishing. At any given instant, the proton contains not three quarks, but something closer to a blizzard of particles. The three valence quarks are there, yes, but surrounding them is a dense fog of gluons, far more numerous than the quarks themselves. At typical probing energies, gluons carry roughly half of the proton's total momentum. They are not minor players. They are not a background effect. They are the dominant population inside the proton, outnumbering the valence quarks many times over. Mixed into this gluon fog are virtual quark-antiquark pairs, flickering in and out of existence on timescales so short that they barely register individually. But collectively, they matter. There are virtual up quarks and up antiquarks, virtual down quarks and down antiquarks. And remarkably, there are even virtual strange quarks and strange antiquarks, particles heavier than up and down quarks that have no role in the proton's identity but appear briefly as quantum fluctuations in the gluon field. The proton contains particles that aren't even part of its definition. They're just borrowed energy, momentary excursions of the quantum vacuum, appearing and vanishing inside the proton's boundaries. If you could somehow freeze the proton at a single instant and count everything inside, you would find three valence quarks, dozens of gluons, and several quark-antiquark pairs, all packed into a volume roughly 1 femtometer across, that same impossibly small distance we encountered moments ago. Everything inside that space is moving at speeds close to the speed of light, interacting furiously, constantly exchanging gluons and creating and destroying virtual particles. It is one of the most energetic environments in the known universe, compressed into one of the smallest possible spaces. And all of this energy, every gluon, every virtual quark pair, every screaming relativistic motion of the valence quarks, contributes to the number you read when you put a proton on a scale. The mass of the proton is the total energy of this entire raging storm, divided by the speed of light squared. Nothing is wasted, nothing is irrelevant. Every fluctuation counts. The picture is overwhelming in its complexity. The proton is not a simple object. It's not three little balls glued together. It's a quantum mechanical system of extraordinary richness, constantly fluctuating, constantly changing its internal configuration, filled with energy in multiple forms. And the mass you measure when you weigh a proton is the total energy of this entire system divided by the speed of light squared. Every form of energy inside the proton contributes. Quark kinetic energy, gluon field energy, quantum fluctuation energy, virtual particle energy. All of it adds up to the proton's mass. Now, how do we know all this is true? How do physicists calculate these contributions and verify them against experiment? After all, the inside of a proton is not something you can photograph or directly observe. Quarks and gluons are permanently confined. You can't extract them and study them one by one. The answer involves some of the most sophisticated mathematical and computational tools in all of science. The theory of QCD is precise and well-defined. Its equations are known, but solving those equations is extraordinarily difficult. The strong force is called strong for a reason. The coupling constant of QCD, the number that measures the strength of the interaction, is large at the energy scales relevant to proton structure. This means the standard mathematical technique used in most quantum field theory calculations, called perturbation theory, doesn't work well here. Perturbation theory works by treating the interaction as a small correction to a simpler system and expanding in powers of the coupling constant. When the coupling constant is small, as it is in electromagnetism, this works beautifully. You calculate increasingly small corrections, and the answer converges quickly. But when the coupling constant is large, the corrections are not small. They're enormous. Each successive term in the expansion is bigger than the last. The method fails completely. To calculate the properties of protons from first principles, physicists use a technique called lattice QCD. The idea is conceptually straightforward, even though the execution is fiendishly complex. You take the equations of QCD and put them on a grid, a discrete lattice of points representing spacetime. Instead of continuous space, you work with a finite number of points separated by small distances. Instead of continuous time, you work with discrete time steps. You then use powerful supercomputers to simulate the behavior of quark and gluon fields on this lattice. The simulation essentially recreates the interior of a proton from the fundamental equations. You put in the known quark masses, the known coupling constant, and the rules of QCD. Then you let the simulation run. The quarks and gluons interact according to the laws of the strong force. They exchange gluons. They fluctuate quantum mechanically. The fields store energy. And out of this simulation, you can extract the total energy of the system, which, by Einstein's equivalence, gives you the mass of the proton. This is not easy. These simulations require some of the most powerful supercomputers on Earth. A single calculation can take months of computing time. The lattice must be fine enough that the discrete spacing doesn't introduce significant errors, but coarse enough that the computation is actually feasible. Physicists must extrapolate to the limit of zero lattice spacing and infinite volume to get physically meaningful results. The process requires immense technical skill and decades of methodological refinement. But the results are stunning. Lattice QCD calculations have reproduced the proton's mass from first principles to within a few % accuracy. More impressively, they've reproduced the masses of an entire spectrum of hadrons, protons, neutrons, pions, kaons, and dozens of others, all from the same fundamental equations with the same input parameters. The masses that come out of these calculations are not put in by hand. They emerge from the dynamics. They are predictions, calculated from the underlying theory, and they match experimental measurements. In 2008, the Budapest-Marseille-Wuppertal collaboration published a landmark result. Using a lattice QCD with unprecedented computational power and, for the first time, physical quark masses with fully controlled uncertainties, they calculated the masses of multiple hadrons, including the proton, and found agreement with experiment across the board. The calculated proton mass matched the measured value almost exactly. It was the first time anyone had derived the mass of ordinary matter from the fundamental equations of the strong force at that level of accuracy. This is one of the great triumphs of modern theoretical physics. We can explain where the proton's mass comes from. We can calculate it. And the answer is clear. The mass comes overwhelmingly from the energy of quark-gluon dynamics inside the proton. Not from the rest masses of the quarks, not from some mysterious substance, from energy generated by the strong force confined within a space smaller than a trillionth of a millimeter. The neutron tells the same story. A neutron contains one up quark and two down quarks, compared to the proton's two up quarks and one down quark. The neutron is slightly heavier than the proton, with a mass of about 939.6 mega-electronvolts divided by the speed of light squared, compared to the proton's 938.3. The tiny mass difference, about 1.3 mega-electronvolts divided by the speed of light squared, arises partly from the slightly different quark composition and partly from electromagnetic effects within the neutron. But the overwhelming majority of the neutron's mass comes from the same source as the protons: energy. Quark kinetic energy and gluon field energy, confined by the strong force, manifesting as mass through Einstein's equivalence. That tiny mass difference between the neutron and the proton, just 1.3 mega-electronvolts divided by the speed of light squared, might seem like an insignificant detail. It amounts to roughly 0.1% of either particle's total mass. But this minuscule difference has staggering consequences for the universe. Because the neutron is slightly heavier than the proton, a free neutron is unstable. It decays into a proton, an electron, and an antineutrino with a half-life of about 10 minutes. This means that in the early universe, as things cooled after the Big Bang, free neutrons gradually converted into protons. If the mass difference were reversed, if the proton were heavier than the neutron, then protons would decay into neutrons instead. There would be no stable protons. And without stable protons, there would be no hydrogen. Without hydrogen, there would be no stars, because stars are powered by hydrogen fusion. Without stars, there would be no heavy elements, no planets, no chemistry, no biology, no life. The entire existence of the universe as we know it depends on the neutron being slightly heavier than the proton. And that mass difference arises from a subtle interplay between the slightly different masses of up and down quarks, which come from the Higgs field, and the slightly different electromagnetic and strong force energies inside each particle. The most consequential mass difference in nature, the one that determines whether a universe can produce stars and life, comes from the very mechanisms we have been discussing. Higgs interactions and QCD energy, working together at the femtometer scale, shaping the large-scale fate of the cosmos. So when you hold anything in your hands, when you feel the weight of any object, what you're really feeling is the energy of the strong nuclear force, locked inside trillions upon trillions of protons and neutrons. Every atom in that object has a nucleus. Every nucleus is made of protons and neutrons. And inside each of those protons and neutrons, quarks are whirling at near light speed, while gluons churn and multiply in a frenzy of strong force activity. All of that energy, all of that violence happening at scales far smaller than any microscope can see, adds up to the mass you feel in your hand. Consider the weight of your own body. If you weigh around 70 kilograms, more than 69 kilograms of that comes from the energy of the strong force inside your protons and neutrons. Less than 1 kilogram comes from the Higgs-given rest masses of your quarks and electrons combined. The overwhelming majority of you, by mass, is not substance. It is energy. Trapped, confined, furious energy, held in place by the strongest force in the known universe. This is perhaps the most counterintuitive fact in all of physics. Mass feels solid. Mass feels substantial. When you pick up a rock, it feels like you're holding something made of stuff, something dense and real and material. But at the deepest level, that sensation of substance is an illusion of scale. What you're actually holding is energy, organized energy, confined energy, energy structured by quantum fields and bound by forces so strong that the energy behaves, for all practical purposes, exactly like solid matter. It responds to gravity. It resists acceleration. It has weight. It has inertia. It does everything mass is supposed to do. Because it is mass. Energy is mass. Mass is energy. Not metaphorically, literally. This brings us to a deeper appreciation of what Einstein's equation, E equals mc squared, really means in this context. The equation is often presented as a formula for nuclear weapons or power plants, a recipe for converting mass into energy. And it does describe that. Nuclear reactions release energy by converting a small fraction of rest mass into kinetic energy and radiation. But the equation works in both directions. It also describes how energy can manifest as mass. And inside every proton and neutron, that is exactly what happens. Energy becomes mass. The energy of the strong force, the energy of quark motion, the energy of gluon fields, all of it contributes to the mass of the proton, not by being converted into some other substance, but by simply being energy. Energy already is mass. They are the same thing, measured in different units, connected by the speed of light squared. When you lift a heavy object, you are doing work against gravity. Gravity pulls on mass, and the mass it's pulling on is, more than 99%, the energy of the strong force inside atomic nuclei. Gravity doesn't care what form the mass takes. It doesn't distinguish between rest mass and energy. It doesn't check whether the mass comes from the Higgs mechanism or from QCD dynamics. Gravity simply responds to total energy. And the total energy of a proton, which includes the rest masses of its quarks, the kinetic energy of their motion, the energy of the gluon fields, and the energy of quantum fluctuations, all of that is what gravity acts on. All of that is what you feel as weight. This is the deep answer to the question we started with. What is the mass of a proton made of? It's not made of smaller stuff. It's made of energy. The energy of quarks confined by the strong force, the energy of gluon fields holding those quarks together, and the energy of the restless quantum vacuum inside the proton's boundaries. Mass, at this level, is not a substance. It is a consequence of dynamics. It is what happens when energy is trapped in a small space by an overwhelmingly powerful force. And this is not speculation. This is not a philosophical interpretation. This is the result of precise calculations using the well-tested theory of quantum chromodynamics, confirmed by lattice simulations on supercomputers and consistent with decades of experimental measurements at particle accelerators around the world. We know where the proton's mass comes from. We can calculate it, and the answer is energy. The implications ripple outward from the proton to everything else. Every atom gets almost all its mass from its nucleus. Every nucleus gets almost all its mass from its protons and neutrons. And every proton and neutron gets more than 99% of its mass from strong force energy. So the mass of everything around you, the floor beneath your feet, the air you breathe, the planet you stand on, the star that lights your sky, all of it is overwhelmingly composed of trapped energy. The ordinary matter of the universe, the matter that forms stars and planets and living things, is more than 99% energy by mass. You are, in the most literal physical sense, a being made of energy. Not in the vague, mystical way that phrase is sometimes used, but in the hardest, most precise, most experimentally verified way physics can offer. The mass of your body is dominated by the energy of the strong nuclear force, confined within protons and neutrons so small that 100,000 of them could span the width of a single atom. And that energy, invisible and violent and relentless, is what makes you substantial. It is what gives you weight. It is what makes you real in the physical sense. Not substance, not stuff. Energy, structured by quantum fields and governed by the laws of quantum chromodynamics. We have now seen the two great mechanisms that generate mass in the physical world. The Higgs field, which gives rest mass to elementary particles like electrons and quarks, through their interaction with a field that fills all of space. And the strong nuclear force, whose ferocious energy inside protons and neutrons generates more than 99% of the mass in ordinary matter. These are two very different mechanisms, operating at different scales, governed by different physics, producing different amounts of mass. And yet they work together to create the world you experience. Now it's time to pull the entire picture together, to step back from the details of quarks and gluons and fields, and ask the simplest, deepest question. What is mass? Not what generates it, not what mechanisms produce it, but what is it? What does it mean for something to have mass? And how should we think about mass now that we know its origins are so much stranger than anyone imagined? Let's start with what mass does, because even if mass has surprising origins, its effects are concrete, measurable, and familiar. Mass does two things in physics. Two distinct, observable things that define what mass means in practice. The first thing mass does is resist acceleration. This is called inertia. When you push something, it pushes back. Not because it wants to, not because it's choosing to resist, but because that's what mass does. The more mass an object has, the harder it is to change its motion. A bowling ball is harder to push than a tennis ball. A truck is harder to stop than a bicycle. A planet is harder to deflect than a pebble. This resistance to changes in motion is the defining characteristic of inertia, and it's directly proportional to mass. Newton captured this in his second law of motion. Force equals mass times acceleration. F equals ma. This equation tells you that for a given force, the resulting acceleration is smaller when the mass is larger. Push a 1 kilogram object with 10 newtons of force, and it accelerates at 10 meters per second squared. Push a 10 kilogram object with the same force, and it accelerates at 1 meter per second squared. 10 times more mass means 10 times less acceleration for the same push. Mass is the measure of how stubbornly an object resists being moved. The second thing mass does is create and respond to gravity. Every object with mass attracts every other object with mass. This is gravitation. The more mass an object has, the stronger its gravitational pull. Earth has a lot of mass, so it pulls you toward its center with a force you experience as weight. The Sun has enormously more mass than Earth, so it pulls Earth into orbit around it. A galaxy contains billions of solar masses, so its gravity shapes the motion of stars across 100,000 light-years. These two properties, inertia and gravity, are what mass means in practice. If you want to know how much mass something has, you either measure how hard it is to accelerate, or you measure how strongly it pulls on other things gravitationally. Those are the two operational definitions of mass, and they always give the same answer. This fact, that inertial mass and gravitational mass are identical, is one of the deepest and most mysterious observations in all of physics. There is no obvious reason why the property that resists acceleration should be exactly the same property that generates gravity. Resistance to pushing and attracting other objects are conceptually very different things. You could imagine a universe where they were governed by different quantities, where something could be very hard to push but gravitationally weak, or easy to push but gravitationally strong. But in our universe, they're the same, always, without exception. Galileo noticed this implicitly when he observed that all objects fall at the same rate regardless of their mass. A heavy cannonball and a light wooden ball, dropped from the same height, hit the ground at the same time, ignoring air resistance. This only makes sense if the property that makes the cannonball harder to accelerate is exactly the same property that makes gravity pull on it more strongly. The two effects cancel perfectly, producing the same acceleration for all objects. Einstein elevated this observation into a fundamental principle. He called it the equivalence principle, and it became the foundation of his general theory of relativity, published in 1915. General relativity describes gravity not as a force pulling objects together, but as a curvature of space-time caused by mass and energy. Massive objects curve the geometry of space and time around them. Other objects then follow the natural paths through this curved geometry, paths called geodesics. What we experience as gravitational attraction is really the effect of curved space-time guiding the motion of objects. And here's the crucial point for our discussion. General relativity doesn't care what form mass takes. It doesn't distinguish between rest mass and energy. It doesn't ask whether the mass comes from the Higgs field or from QCD dynamics. General relativity responds to total energy. Whatever energy a system contains, from whatever source, that energy curves space-time. That energy generates gravity. That energy resists acceleration. This means the energy of the strong force inside your protons and neutrons curves space-time exactly the same way that rest mass does. The gluon field energy inside a proton gravitates. The kinetic energy of confined quarks gravitates. Every form of energy contributes to gravity and to inertia, without exception. There is no second-class mass. There is no distinction between real mass and energy-derived mass when it comes to how the universe actually behaves. Mass from the Higgs field and mass from QCD energy are equally real, equally measurable, equally consequential. When Earth orbits the Sun, the gravitational force holding it in orbit comes from the total mass of both objects. And more than 99% of that mass, for both Earth and the Sun, is strong force energy inside protons and neutrons. The gravity that keeps you on the ground, the gravity that holds the Moon in orbit, the gravity that shapes galaxies and bends light around black holes, all of it is overwhelmingly generated by energy, not by the Higgs-given rest masses of elementary particles. This brings us to a distinction that is easy to confuse, but essential to understand. The distinction between mass as a measured quantity and mass as a physical origin. When you step on a scale, you measure mass. The number it gives you is a single quantity, your mass. Roughly 70 kilograms, perhaps. That number is straightforward. It tells you how hard it is to accelerate you and how strongly you pull on the Earth gravitationally. It's a clean, precise, singular measurement. But behind that single number are multiple physical origins working together. Part of your mass comes from the Higgs-given rest masses of your electrons, a tiny part. Part comes from the Higgs-given rest masses of your quarks, also tiny. The overwhelming majority comes from the energy of quark-gluon dynamics inside your protons and neutrons. And there are even smaller contributions from electromagnetic energy binding electrons to nuclei, from the nuclear binding energy holding protons and neutrons together in atomic nuclei, and from the kinetic energy of molecular motion. All of these contributions add up to your total mass, but they come from different mechanisms. They have different physical origins. The measured quantity is one number. The physical origin is a complicated mixture of field interactions, binding energies, and dynamic processes. This is why the question, what is mass made of, doesn't have a simple answer. Mass isn't made of any one thing. It isn't a substance you can isolate and point to. It's a measurable property that emerges from the total energy content of a system, with contributions from multiple sources. Asking what mass is made of is a bit like asking what temperature is made of. Temperature isn't made of anything. It's a property of a system, arising from the kinetic energy of the particles within it. You can measure temperature precisely. You can feel it. It has real physical effects. But it isn't a substance. It doesn't have a material composition. It's a property, not a thing. Mass is similar. It's a property of particles and systems. It arises from field interactions and energy content. It's real. It's measurable. It has profound physical consequences. But it is not a substance. It's not made of smaller stuff. It emerges from the deeper workings of quantum fields and forces. Now, let's address some common misunderstandings directly, because the story of mass is often told in ways that leave people with incorrect impressions. First, mass is not an illusion. Sometimes, when people hear that mass comes from energy rather than substance, they conclude that mass isn't real, that it's somehow fake or illusory. This is completely wrong. Mass is as real as anything in physics. When a proton sits on a scale, it has a definite, measurable mass. When you drop a rock, it falls because of its mass. When a star collapses into a neutron star, the mass is what drives the collapse. The fact that mass originates from energy and field interactions doesn't make it less real. It makes it more interesting. A wave on the ocean is not an illusion just because it's made of water rather than being a separate object. The wave is real. It carries energy. It can capsize a boat. Similarly, mass is real. It curves space-time. It resists acceleration. The fact that it emerges from energy doesn't diminish its reality in the slightest. Second, mass does not all come from the Higgs field. This is perhaps the most widespread misconception in popular physics. Many people believe the Higgs field is the source of all mass in the universe. It is not. The Higgs field gives rest mass to elementary particles, and those rest masses account for less than 1% of the mass of ordinary matter. More than 99% comes from the strong force energy inside protons and neutrons. The Higgs field is essential, absolutely essential, for the existence of matter as we know it, because without it, electrons and quarks would be massless and could never form atoms. But the Higgs field is not the main source of mass in the universe, not even close. Third, mass is not made of Higgs bosons. We covered this distinction earlier, but it bears a brief reminder. The boson is a ripple in the field, not the source of mass itself. But there's a related misconception worth addressing separately. Some people hear that the Higgs field gives particles mass and picture something like friction, as though the field is slowing particles down and that resistance is what we call mass. This is misleading. The Higgs interaction does not slow particles down. It does not drain their energy. An electron moving through the Higgs field does not gradually decelerate the way a ball rolling through mud would. Instead, the interaction changes the electron's fundamental relationship with space-time. It transforms a particle that would otherwise travel at light speed into one that can exist at rest. That is a very different thing from friction. Fourth, mass is not generated by a single mechanism. There is no one answer to where mass comes from. Elementary particle rest mass comes from the Higgs field. Composite particle mass comes predominantly from binding energy and internal dynamics. Nuclear mass includes contributions from nuclear binding energy. Atomic mass includes tiny contributions from electromagnetic binding energy. Molecular mass includes even tinier contributions from chemical binding energy and kinetic energy of constituent atoms. Each level of organization adds or subtracts a little mass through different physical processes. Mass is the sum of all these contributions, a composite quantity with multiple origins. And there are forms of mass whose origins we do not yet understand at all. Neutrinos, for decades, were assumed to be completely massless. The original Standard Model predicted zero mass for neutrinos, but experiments in the late 1990s and early 2000s proved otherwise. Neutrinos oscillate between three types, or flavors, as they travel through space. An electron neutrino can transform into a muon neutrino or a tau neutrino and back again. This oscillation is only possible if neutrinos have mass. The masses are confirmed to be non-zero, but neutrino masses are extraordinarily tiny. The heaviest neutrino has a mass less than about 1 electron volt divided by the speed of light squared. Compare that to the electron, which has a mass of about 511,000 electron volts divided by the speed of light squared. Neutrinos are at least 500,000 times lighter than the electron, which is itself an extremely light particle. Why are neutrino masses so incredibly small? And do they even come from the Higgs field at all? This is an open question. The Standard Model, in its original form, doesn't include neutrino masses. They have to be added by hand, and there are multiple theoretical ways to do it. One possibility is that neutrinos interact with the Higgs field just like other particles, but with coupling constants so absurdly small that the resulting masses are tiny. Another possibility, favoured by many theorists, is that neutrino masses arise from a completely different mechanism. A mechanism involving hypothetical ultra-heavy particles that have never been observed, called right-handed neutrinos. In this picture, the smallness of neutrino masses is explained by the extreme heaviness of these unseen partners. The heavier the partner, the lighter the observable neutrino. This is called the seesaw mechanism, and if it's correct, it means there is a third mass-generating mechanism in nature, beyond the Higgs field and beyond QCD energy. A mechanism we haven't directly detected yet. Then there is dark matter. Observations of galaxies, galaxy clusters, and the large-scale structure of the universe have revealed that about 85% of all mass in the universe is not ordinary matter. It is something else. Something that has mass, that gravitates, that shapes the rotation curves of galaxies and bends light around galaxy clusters, but that does not interact with light and has never been directly detected in a laboratory. We call it dark matter because we cannot see it. We know it has mass. We can measure its gravitational effects with extraordinary precision, but we do not know what it is made of. We do not know what mechanism gives it mass. We do not know whether dark matter particles interact with the Higgs field or whether their mass comes from some entirely unknown source. This means that when we say we understand where mass comes from, we need to be honest about the limits of that understanding. We understand the mass of ordinary matter very well. We can calculate proton masses from first principles. We can explain the Higgs mechanism in precise mathematical detail. But ordinary matter accounts for only about 15% of the total mass in the universe. The other 85% is dark matter, and its mass remains unexplained. There's also the mystery of the Higgs couplings themselves. The Higgs field gives different particles different masses because it couples to each particle with a different strength. The electron couples weakly, so it's light. The top quark couples strongly, so it's heavy. But why? Why does the top quark couple roughly 338,000 times more strongly than the electron? Is there a pattern? A deeper principle? A reason these numbers are what they are? The Standard Model offers no answer. It accepts the coupling constants as measured inputs. It does not predict them. Understanding why the masses of elementary particles have the specific values they do remains one of the great unsolved problems in fundamental physics. It is entirely possible that answering this question will require physics beyond the Standard Model, perhaps a deeper theory that explains the Higgs couplings the way the Higgs field itself explains mass. Fifth, and this is subtle but important, the connection between energy and mass should not be reduced to a slogan. You sometimes hear people say, mass is just energy, as if that settles the question. But this oversimplifies a nuanced relationship. Mass and energy are related, deeply and precisely through Einstein's equations. But they are not identical concepts. A photon has energy, but no rest mass. A system of two photons moving in opposite directions has more rest mass than either photon alone, because the system has energy that cannot be removed by changing your reference frame. Rest mass is the energy a system has in its own rest frame. It's a specific, well-defined quantity. Total energy depends on your reference frame. Rest mass does not. They're related but distinct concepts, and conflating them leads to confusion. With all this in mind, let's construct the complete picture of where mass comes from in ordinary matter. The matter that makes up you, the Earth, the stars, and everything you interact with in daily life. Start with an atom. Any atom. Let's say an atom of carbon, one of the most common elements in your body. A carbon atom has 6 protons and 6 neutrons in its nucleus, surrounded by 6 electrons. The 6 electrons have rest masses given by the Higgs field. Each electron has a mass of about 0.511 mega-electron-volts divided by the speed of light squared. 6 electrons contribute roughly 3.1 mega-electron-volts divided by the speed of light squared. That's a tiny amount compared to the total mass of the carbon atom, which is about 11,178 mega-electron-volts divided by the speed of light squared. The electrons contribute about 0.03% of the atom's mass, essentially nothing. The nucleus contains 6 protons and 6 neutrons. Each proton has a mass of about 938.3 mega-electron-volts divided by the speed of light squared. Each neutron has a mass of about 939.6 mega-electron-volts divided by the speed of light squared. If you simply added up 6 proton masses and 6 neutron masses, you'd get about 11,267 mega-electron-volts divided by the speed of light squared. But the actual mass of a carbon-12 nucleus is about 11,175 mega-electron-volts divided by the speed of light squared. That's less than the sum of its parts by about 92 mega-electron-volts divided by the speed of light squared. Where did that mass go? It went into binding energy. When protons and neutrons come together to form a nucleus, they release energy. The strong nuclear force binds them together, and the system loses energy in the process. Since energy and mass are equivalent, losing energy means losing mass. The nucleus weighs less than the sum of its free protons and neutrons. The missing mass, called the mass defect, is the binding energy that was released when the nucleus formed. This is the energy that powers stars. Nuclear fusion in the Sun's core combines lighter nuclei into heavier ones, releasing binding energy as radiation. That radiation is what lights the sun and warms the Earth. The mass defect is real, it's measurable, and it shows that even at the nuclear level, mass is not simply the sum of its parts. The interactions between parts, the energies involved in binding them together, add or subtract from the total. Now look deeper. Inside each of those 12 nucleons, the 6 protons and 6 neutrons, the story we have just explored plays out. The quarks have Higgs-given rest masses contributing less than 1%. The remaining 99+% comes from QCD energy. The kinetic energy of quarks, the energy of gluon fields, and the energy of quantum fluctuations all contribute. So the mass of the carbon atom comes overwhelmingly from the energy inside its nucleons. A small subtraction comes from nuclear binding energy. An even smaller addition comes from the rest masses of its electrons. And a vanishingly small contribution comes from the electromagnetic energy binding the electrons to the nucleus. This hierarchy holds for every atom of every element. The mass of ordinary matter is dominated by nuclei. The mass of nuclei is dominated by nucleons. The mass of nucleons is dominated by strong force energy. And the Higgs-given rest masses of quarks and electrons are a tiny fraction of the whole. This is the structure of mass in the everyday world. Let's zoom out even further. Consider a large object like the Earth. Earth has a mass of about 5.97 times 10 to the 24th kilograms. Virtually all of that mass is in atomic nuclei. Electrons contribute a negligible fraction. The nuclear binding energies, which reduce the mass slightly compared to free nucleons, represent a small correction. And the thermal energy of the atoms, their kinetic energy of motion, adds an even smaller amount. The Sun is similar, but with an important wrinkle. The Sun is actively fusing hydrogen into helium in its core. This process converts some rest mass into radiant energy. Every second, the Sun converts roughly 4 million tons of mass into energy through nuclear fusion. This energy radiates outward as sunlight. The Sun is literally getting lighter over time, losing mass as it shines. The mass it loses is the mass defect of the fusion reactions, the difference in binding energy between the lighter nuclei going in and the heavier nuclei coming out. Over its entire lifetime of roughly 10 billion years, the Sun will lose about 0.07% of its total mass through fusion. A small fraction, but an enormous amount of energy. This process beautifully illustrates the interplay between mass and energy. The Sun's mass generates the gravity that compresses its core. The compression raises the temperature high enough for fusion. Fusion converts mass into energy. That energy radiates into space, warming planets, driving weather, powering photosynthesis, sustaining life. The mass of your body, which is mostly strong force energy inside nucleons, was assembled from atoms forged in stellar cores, where nuclear binding energy was rearranged and released as light. Mass, energy, and the forces of nature are woven together at every level. Think about the full circle of what we've described. The mass of a star like the Sun comes overwhelmingly from the energy of the strong force inside its protons and neutrons. That mass generates the gravitational pressure that compresses the star's core until hydrogen nuclei fuse into helium, releasing binding energy as light. That light travels across space and sustains life on a rocky planet orbiting nearby. The atoms in that planet, and in every living thing on its surface, were themselves forged inside earlier generations of stars that lived and died billions of years ago. Those atoms carry mass for the same reason the star's atoms did, not because of substance, but because of energy, the same QCD energy, the same confined quarks and churning gluons operating inside every proton and neutron in every atom that has ever existed. The mass that builds stars is the same mass that builds you, and in both cases it is energy, not stuff, doing the building. So what is mass? After everything we've explored, here is the most honest and complete answer physics can give. Mass is a measurable property of particles and systems. It is not a substance. It is not made of a single thing. It does not have one origin. For elementary particles like electrons and quarks, rest mass arises from interactions with the Higgs field. For composite particles like protons and neutrons, mass arises predominantly from the energy of internal dynamics, specifically the kinetic energy of confined quarks and the energy stored in gluon fields. For atoms, mass is overwhelmingly the mass of the nucleus, slightly reduced by nuclear binding energy. For large objects, mass is the sum of atomic masses, with tiny corrections from thermal energy, gravitational binding energy, and other effects. At every level, mass emerges from fields, energy, and interactions. It is never just stuff. It is always a consequence of deeper physics. And yet, it is completely real. It curves space-time. It resists acceleration. It falls in gravitational fields. It determines the structure of atoms, the formation of stars, the shape of galaxies, and the evolution of the universe. There is something profoundly humbling about this understanding. For thousands of years, humans believed mass was the most fundamental, most basic, most irreducible property of matter. It was the ultimate stuff. You could break an object into pieces, and each piece had mass. You could break those pieces into atoms, and each atom had mass. Mass was always there, at every level, solid and irreducible and simple. It seemed like the one thing you could always count on, the one property that never needed explaining. Things had mass because they were made of stuff, and stuff had mass because it was stuff. Quantum physics showed us otherwise. Mass is not fundamental in the way we thought. It is not irreducible. It is not simple. It has origins, mechanisms, and explanations. The mass of the electron comes from the Higgs field. The mass of the proton comes from strong force energy. The mass of an atom comes from its nucleus. Each layer has its own explanation, its own mechanism, its own physics. And at the bottom, there is no ultimate stuff. There are quantum fields and excitations of those fields, and interactions between those excitations, and energy generated by those interactions. Mass is what we measure when we add it all up. The universe is not made of stuff. It's made of fields. Quantum fields filling all of space, vibrating and interacting and exchanging energy according to precise mathematical laws. And mass, the most tangible, most solid feeling property of the physical world, is one of the things those fields produce. Not by being material, not by being substance, but by interacting, by confining energy, by breaking symmetries, by doing what fields do. You are sitting right now in a sea of quantum fields. The electron field, the quark fields, the gluon field, the electromagnetic field, the Higgs field. They permeate every point in space. They are here, right now, filling the room, filling your body, filling the spaces between stars. And the mass you feel when you stand up, the weight that presses your feet against the floor, the heaviness of your own body under Earth's gravity, all of it is these fields at work. The Higgs field, giving your electrons and quarks their tiny rest masses. The gluon field, generating the overwhelming majority of your mass through sheer confined energy. Gravity, curving space-time in response to all that energy, pulling you toward the center of the Earth. You are a pattern of quantum fields, a temporary, beautiful, conscious pattern of vibrating fields, held together by forces, given mass by energy, given substance by interactions so deep and so fundamental that they are woven into the fabric of every quantum field filling the space around you right now. And the mass you feel, the weight of your existence, the heaviness of the world, is the signature of those fields. It is quantum physics, written in the language of everyday experience. It is the deepest nature of reality, translated into the simple sensation of holding something heavy in your hands. Mass is not what you thought it was. It is something far more extraordinary. It is not the amount of stuff inside an object. It is the energy of fields and the consequences of their interactions, measured as a single number, felt as a single sensation, but arising from a tapestry of quantum processes so rich and so intricate that understanding them has taken the greatest minds in human history more than a century of effort. And we are still learning. The next time you pick up a stone, feel its weight, and think about what's inside it. Remember this: more than 99% of the mass in your hand is not substance. It is energy, trapped energy, furious energy, energy confined by the strongest force in nature within spaces smaller than a trillionth of a millimeter. Energy that manifests as weight, as solidity, as the feeling of something real in your grasp. That is what mass is made of, according to quantum physics. Not stuff, fields, not substance, energy. Not simplicity, profound, beautiful, irreducible complexity, hiding behind the most familiar sensation in the world. And consider what this means for how you see the world around you. Every object you encounter, every surface you touch, every meal you eat, all of it is held together and given substance by quantum processes operating at scales you will never directly perceive. The chair beneath you feels solid, but its solidity is the electromagnetic repulsion between electron clouds in adjacent atoms. Atoms whose mass is almost entirely the energy of quarks and gluons, confined within nuclei too small to see with any microscope ever built. The ground beneath a building feels firm and unyielding, but its firmness arises from the same quantum fields, the same strong force energy, the same Higgs interactions that operate inside every proton in the universe. There is no boundary between the exotic physics of quantum fields and the mundane reality of everyday experience. They are the same thing. The quantum world is not a distant, abstract realm accessible only to physicists with particle accelerators. It is the world. It is this world. The weight of your morning coffee, the resistance you feel when you push a door open, the force you exert climbing a staircase. All of it is quantum field theory, expressed in the language of daily life. And perhaps the most remarkable thing of all is that we figured this out. Humans, living on one small planet, using nothing but careful thought and clever experiments, uncovered the origins of mass. We looked at something so familiar it seemed to need no explanation. The heaviness of objects, the effort of lifting, the pull of gravity. And we asked, why? We asked what mass really is. We followed the question through centuries of discovery, through atoms and nuclei and quarks and gluons, through the Higgs field and quantum chromodynamics, and Einstein's equivalence of energy and mass, until we arrived at an answer that nobody expected. Mass is not stuff. It is fields and energy structured by forces, emerging from interactions, real and measurable and consequential, but far stranger and far more beautiful than the simple substance we once imagined it to be. That answer is not the end. There are still questions we cannot answer, Why do the fundamental constants have the values they do? What gives dark matter its mass? Is there a deeper theory beneath the standard model that explains the pattern of particle masses? These questions remain open. They drive the next generation of experiments, the next generation of theories, the next generation of physicists who will carry this story forward. But what we have already learned is extraordinary. We know that when you hold something heavy in your hand, you are holding trapped energy. You are feeling the consequences of quantum fields interacting at scales smaller than a trillionth of a millimeter. You are experiencing, in the most direct physical way possible, the deep structure of reality itself. And that knowledge, hard-won over more than a century of human effort, is one of the greatest achievements of the human mind. We asked what mass is made of, and the universe answered with something no one imagined. Not substance, not stuff, but fields and energy, and the beautiful, relentless dynamics of the quantum world.